Steinhauer here, welcome back. Continue our discussion of brightness and luminosity, specifically of stars in the galaxy. We have talked about magnitudes already and talked about how brightness and luminosity are related. And you might think that the magnitude is the only crazy way of measuring things in astronomy, but you're sadly mistaken. Because the magnitude that we referred to before was the apparent magnitude. It is how bright a star appeared to us. But there is another magnitude that is related to an object's luminosity, and that is the absolute magnitude. So again, apparent magnitude relates to how bright a star appears, and absolute magnitude refers to how luminous an object is. And just like brightness and luminosity, apparent magnitude is going to depend on how far or close that star is to us, but a star's absolute magnitude will not be dependent on how far that star is from us. It's an intrinsic property of that star. And the equation for absolute magnitude is almost exactly the same as the equation for apparent magnitude. If we were to write it out, it would look like this. M1 minus M2 equals negative 2.5 times the log, base 10, as always, of, instead of the ratio of the brightnesses, this is the ratio of the luminosities. L1 over L2. To distinguish between apparent and absolute magnitude, it's kind of difficult to tell with my handwriting, but these are capital M's for absolute magnitude, and we'll use lowercase m's to refer to apparent magnitudes. Now, how is this defined? This is defined such that the absolute magnitude of a star is the apparent magnitude that a star would have if it were exactly 10 parsecs away from us. So again, it doesn't matter what that distance is, but if that object were 10 parsecs away from us, then its apparent magnitude and its absolute magnitude would be exactly the same. Okay, so just like there is a relationship between the brightness of an object and its luminosity and the distance, there has to be a relationship between the apparent magnitude of an object, its absolute magnitude of the same object, and the distance to that object. And that is the next slide. This is called the distance modulus equation. And this is a little bit different. This is similar to what we've seen before in terms of magnitude relationships, but the apparent and absolute magnitudes were almost always comparing different objects. The magnitude of one object minus the magnitude of a second object. The absolute magnitude of one object minus the absolute magnitude of another object. This relationship compares the apparent and absolute magnitude of a single object and how they're related to the distance to that object. And this is the equation. The apparent magnitude, lowercase m, minus the absolute magnitude, uppercase M, is equal to 5 times the log of the distance, again, base 10, minus 5. And this is one of those equations, again, where the distance in this case has to be in parsecs. And this equation can be derived directly from the magnitude equation and the definition that the absolute magnitude is the apparent magnitude if the object were at 10 parsecs away. So just so you know, if you were to, the order of operations holds here, but if you were to put a parentheses here, it would be this. So if you're doing this in order, you have to take the log first of the distance, and then multiply it by 5, and then subtract 5. If you take d minus 5 and take the log first, you will get the answer wrong. So again, the order of operations are logs first, then multiply, then you can do addition and subtraction. Okay, so let's try this equation out. A star is 1,000 parsecs away and has an apparent magnitude of 11.6. What is its absolute magnitude? Well, let's write our equation down and see if we can figure this one out. Big M, little m minus big M is equal to 5 times the log of the distance minus 5. Well, we know that distance is 1,000, 5 times the log of 1,000 minus 5. What is the log of 1,000? Well, 1,000 is actually an easy one. You might not even need your calculator for this. The log of 1,000, you just count the zeros, is 3. So this is equal to 5 times 3 minus 5. Well, 5 times 3 is 15, minus 5 is 10. So let's continue this up here. The apparent magnitude minus the absolute magnitude is equal to 10. So now we can solve. We know that the apparent magnitude is 11.6. We can solve this for the absolute magnitude. Let's do the algebra first. We can say, again, we want to get m by itself on one side of the equation. So let's add m to both sides. That will get it positive, and on the other side, big M minus little m, big M minus big M on the left cancel out. And now we can subtract 10 from both sides. And the 10s cancel out over here. And what do we get? We get little m minus 10 on this side and big M on this side. And since we know that apparent magnitude, little m, is 11.6, we can plug that in now and find that big M equals 11.6 minus 10, or big M equals 1.6. So the absolute magnitude of this particular star is 1.6. And so we want to compare that, that doesn't, out of context, that means nothing, a 1.6 apparent magnitude, absolute magnitude. So is it more or less luminous than the sun? The sun's absolute magnitude is about plus 4.8. Again, its apparent magnitude is much brighter than that because it's so close to us. But if the sun were 10 parsecs away from us, its apparent magnitude would be 4.8. It would be one of the fainter stars in the sky. So is this star that we're talking about with a distance of 1,000 parsecs and an apparent magnitude of 11.6, more or less luminous than the sun? It's more luminous. And this is confusing, but again, the absolute magnitude is a logarithmic and inverse scale. So the smaller the number, the more luminous the object. Okay, here's another one to try. A star has the same absolute magnitude of the sun and has an apparent magnitude of 12.2. What is the distance to this star in parsecs? Again, I want you to pause the video and work on it because this is going to be good practice for the homework this week. So go ahead and work on it and then come back and we'll do it together. Okay, welcome back. It's the same equation as we had before. So let's write that down, the distance modulus. By the way, this is called the distance modulus equation because this term, the apparent magnitude minus the absolute magnitude, is sometimes referred to as the distance modulus of that star. It's related, obviously, to the distance. The bigger the distance to the star, the bigger this little m minus big M term is. So this is equal to 5 times the log of the distance minus 5. This time, we don't know what the distance is. We're going to have to solve this for distance. So let's plug our numbers in. We know that the apparent magnitude is 12.2. So that's little m, 12.2. That's way too thin. 12.2 minus the absolute magnitude, which is 4.8, is equal to 5 times the log of the distance minus 5. Great. 12.2 minus 4.8. You can plug that in your calculator. It's 7.4 equals 5 times the log of the distance minus 5. What are we going to do now? Well, we have to unpack this one at a time, right? And we have to get rid of the minus 5 before we can do anything else. So let's add 5 to both sides. The 5's over here, minus 5 plus 5 will go away. 7 plus 5 on the other side is 12.4. And that's equal to 5 times the log of the distance. Great. Now, how do you get rid of this 5? Well, this is a multiplicative factor on this log d, so we have to divide by it. The 5's cancel out over here, and we get that the log of the distance is equal to 12.4 divided by 5, which is 2.48. All right, now how do we get rid of this? How do we solve for d if we know that the log of the distance is 2.48? All right, this is a little bit tricky, but this is where you have to remember how to get rid of this log. And you do that by taking 10 and raising it to the power of both sides. 10 to the log base 10d is d. That gets rid of the log. And this is going to be equal to 10 raised to the power of 2.48. And again, that's a number you're going to need your calculator for. But before you plug it into your calculator, you should think about what that answer should be. You should know that 10 to the 2 is 100 and 10 to the 3 is 1,000. So when you plug it in your calculator, you should get a number that's between 100 and 1,000. And in fact, you should get that the answer is 302 or so. Now, what are the units on this? Again, this is one of those equations where the distance always has to be in the right unit. And the unit in this case is parsecs. So this star will be 302 parsecs away from us. Okay, we'll come back. That's all I need to say about luminosity and brightness. We'll come back in the next video and talk about how to measure the temperatures of stars at their surfaces. See you then.